Okay, so we start with this new topic now, and title is numerical solution of algebraic equations. Okay, now there are basically two methods, two families of numerical methods. One is called direct method, the second is called iterative method. Okay, so first we will discuss about direct method. Direct method is a Gaussian elimination. You are aware of that, and we will discuss something about that also, which can be used to solve the resultant matrix. And there are other methods like Cramer's rule for matrix inversion. So once there is a possibility that either you do by Gaussian elimination method or you use Cramer's rule for matrix inversion. Both are same. Or then there is another called Thomas algorithm for tridiagonal matrix algorithm. It is called TDMA. It is known by TDMA, tridiagonal matrix algorithm. Okay, and it is also called Thomas algorithm. And for one-dimensional situations, now yesterday we were talking about when there are one-dimensional and you have only central difference method is used, so you have only 2 points, left and right. So if you are using only 2 points, left and right, then the matrix you will get is tridiagonal, because for each unknown there will be, for each cell there will be two unknowns, two knowns, right? So two adjacent variables will be there. So basically that will become a tridiagonal matrix. Now the Thomas algorithm actually uses a technique in which this advantage is taken care of, but they are all similar. So let us talk by one. First is your direct method or Gaussian elimination method. Now this all will be available in the books or on the internet. They are available. Now, so this is one of the most basic method. And how do you do it? You write an equation like this in this form: a phi is equal to b, where phi is actually unknown variable and it is a matrix. It is actually column matrix. Phi is a column matrix, single column. So phi is phi 1, phi 2, phi 3 and so on. Okay, this is your matrix on the left side, A matrix. Now basic technique adopted in the algorithm is to eliminate the elements below the diagonal by employing multiple row operations and obtain a new matrix with its elements in the lower triangles equal to 0. So in Gauss elimination method, what we are doing is, this is our diagonal, principal diagonal it is called, and we try to do row operations to make all these elements 0. Okay, so all the elements below this are 0. So this is how we do the row operations. Okay, and then what happens that in the last equation you will find there is only one unknown. So you start backward substitution, you start finding the values from the lower side. So this is a technique, we will see it. Simple technique, only you have to remember few steps here. So what we do is, you know the row operation. You will multiply. How do we remove this? If suppose this we have to remove, what we have to do, row 1 is multiplied by A21, A21 and divided by A11. The whole row, the row operations mean you have to do it for the whole row including the column B. Okay. Then you subtract row 2 minus row 1. From row 2 you remove the row 1, that is, you can say modified row, and you get, this gives you A21 dash equal to 0. I am not saying A21 equal to 0, I am saying A21 dash. That means the new element which you will get will become 0. So this is how you do the row operations. Okay. The elements of the first row of the matrix are multiplied by this A21 divided by A1 and subtracted from the corresponding elements of the second row. Now row operation means you can, if you have to multiply or divide, all the elements of a row have to be multiplied or divided. Only then the equation remains same. You consider it as an equation. Okay. And then you can subtract one equation from the other. So second row is the second equation. Okay. So you can multiply any equation by any number, any constant, you can divide by any constant. Okay. And similarly, you can subtract any row from any row. So the nutshell is all the diagonal, lower diagonal elements are made 0. Okay. The procedure is applied to subsequent rows also. So you are doing for others. Thus that all the elements in the first column A31, 41, A1 are reduced to 0. And the same thing you will do for the second column, third column and fourth column also. Okay. The same procedure is applied for second column and further on. Now what we are doing, this is our, you can say, this process is called forward elimination process. This process is called forward elimination. The upper triangular system of equation can now be solved by the backward substitution method. Now you will find that this is the matrix which you will get, and the last row has only one element. So this row, if you solve, it will give you phi n. This will give you the value of phi n. Now use the value of phi n in this equation, phi n minus 1 and phi n. Now phi n is known, so this will give you phi n minus 1. This is how you keep on doing it. Okay. So variable phi I is solved in reverse order. This is called backward substitution, which means you will solve phi n first, then phi n I n minus 1, phi n minus 2 and so on. This becomes your explicit formulation. Okay. Because you are solving the last row explicit. Now the value of the last row you are using for the previous row. So you keep on doing it. Now the last element will be equal to this. Phi n will be equal to Bn divided by An n. Now let me write here, okay, because this is after the operations. You see, this is the, we have done k row operations here. We are not writing it because superscript as k. Okay, no problem, because unnecessarily not making it complex. So because if you note, we have started with the matrix where the elements were A11. Now you see here we have written 1, superscript as 1. This means that we are starting from this. This is the starting matrix, right? And you will keep on doing it. For each time it will, value will change. So finally you come to nth operation. I have said it as k because n is there already being used. So you can say k after k operations, right? Or rather there will be n operations, because you are doing removing, will there be n? There may be more. So after k operations you get a matrix of this shape. Okay. So your phi n will be equal to bn k divided by a ak nn, or you may write a nn, whatever you want to write. K is representing, that is after the row operation what you are getting. Okay. Now if you want to find out the other elements, okay, this is phi I, where I is less than n, that means from the not the last one but the previous one. So it will be equal to this bi, and of course there will be kth value here, and then you will subtract this from here. This is, you can write it, I am writing a n, you can write k here, right? So the next equation will have only two unknowns. Each equation will have only two unknowns. It's a tridiagonal matrix. We have, not two unknowns, it will be, next will have two, then it will have three, and then it will have four, and so on. But each time only one is unknown. Okay, remaining we have found out. So this is the, you subtract this series from here and you get phi I. So this way you can keep on getting. It's a simple mathematics. When you write in this form, in a condensed form, it looks like complicated, but otherwise it is simple. You are doing Gauss elimination method, you are doing forward elimination, backward substitution. You can see that if you have any doubt. Okay. Now then we talk about Thomas algorithm. Okay. So Gauss elimination method was when all the elements are filled up. Okay. In this case, we have talked about this as sparsely populated matrix. Now these matrices are of this shape. If you look at them, you will find that there are only three x's which are filled up. Remaining all are zeros. Okay, and these are your variables, these are your right side known values. Okay. Thomas algorithm is nothing but simply a Gaussian elimination method applied to sparsely populated matrix. So the same method you are applying to now this sparsely populated TDMA, tridiagonal matrix. Okay. So what we are doing here is considering a truncated version of this matrix. We are assuming that our matrix is like this, just to show the steps, otherwise it will become too bulky. The first step you do, you divide the first row by A11. So divide by A11 or row 1. Okay. Then this is changed, this becomes 1, this becomes modified, and this is also modified. Okay. Then what you do, you subtract. Now what you are doing, subtract A21 multiplied by first row. Okay. So this is what you will get. This will become 0, and this will come out element like this, and this will come on. Nothing happens to the third row. Nothing happens. Okay. Then what you will do, you will convert this term into 1. This term is converted A22 dash. Now this is A22 dash. is converted to 1. So you divide it by this. So you divide the whole row. So you are dividing row 2. You are dividing by A22 dash. Remember, I am writing A22 dash because A22 has changed. Okay. So you are dividing by here, and as well as you are dividing here. Okay. Then what you will do again, this will become, okay, now you are writing it in a, so this has changed, this has also changed. B2 dash. Now you subtract, so you get this 0, and so you subtract row 2 multiplied by A32, and you get this, and finally you divide this also, you get 1 1 1. So you basically get a matrix like this, right? Here also the same thing, forward elimination and backward substitution. Same procedure, only thing Gauss elimination, because all the elements are filled up, you have to do for all the lower elements. Here, because there are only 3 diagonals which are filled up, and you have to make the left diagonal, the lower diagonal, 0. The central diagonal will remain as it is, the upper diagonal will remain as it is. Of course, in row operation they will get modified, but you are not displacing them, you are not making them 0. Only the lower diagonal elements are being made 0. Okay. So this process is carried out depicted in 3 by 3 matrix. Okay. Consequently, we have, okay, in the forward elimination process, the neighboring entries below and left of the diagonals are converted to 0 by simple row operations. Okay, that we have seen it. Now, this is the, if you want to do it mathematically, this is the first row, second element, okay, revised value of this 1 2, A12 is revised like this, and B1, this is row 1. Okay. And similarly, so this is the member of the upper diagonal 1 2. Similarly, these are upper diagonal. So we are giving a formula for upper diagonal members and for B. You can follow this formula because computer will do this formula. It will be difficult for you to do it mentally, right? Filling the values. Normally how we do it, we solve at each step and then continue. Computer has to follow a formula. So this is the formula is there. Okay. The second stage simply involves the back substitution process, which involves evaluating phi s. So phi n will be equal to what? B n dash. B n is a revised one, and similarly phi I, where I is less than n, that means you are going upward, less than n, will be B I dash minus these values. Now remember, there was a series when you were doing Gauss elimination, because there all the upper diagonals were filled up, so you have to take up all of them to the right. Here there is only one diagonal at the top, upper side, so you have only one term to be taken to the right side. Okay, so this is how it can be seen that Thomas algorithm is more economical than Gaussian elimination because of the structure of the tridiagonal matrix. So there is nothing special about this except that being a sparsely populated matrix, this is going to be faster. Okay. Now there is one catch here, that nevertheless, in order to prevent ill conditioning and hence round of error. Now there is a possibility, if these numbers are not properly placed, right, your round of errors may blow up like anything. If some of the diagonal, remember that if any of the diagonal members become 0 or very small, then it has a very large effect on the whole calculation. So what it says that you should have a matrix like this, where the principal diagonal element is quite large than the sum of both left and right elements. This is what is required. Now if that is not the case, you can actually change the rows and do it. So you have to do the conditioning of the matrix. Now these are the things, because we are not going into them, but these are the things which are actually, when you are solving these equations, you might stuck up at some places. Okay. We have only known the process how to solve it. But what are the pitfalls? Technique is simple, but what are the pitfalls? Because while doing a solution, there is a possibility that we are stuck up at some place, because this is not well formed matrix. Nothing wrong with the matrix, but because we are doing computation on computers, this may lead to a problem. So we have to check up that, right? So this is that diagonal coefficients are required to be much larger than the sum of the neighboring coefficients. Okay. Now we take the example, the same example. Yesterday we did it. Yesterday we were doing this example. Okay, now this matrix is to be solved. This is a tridiagonal matrix. This is to be solved by TDMA, okay, according to Thomas algorithm, and this is how it will change. The diagonal elements will become 1, okay, by after row operations, and then you can solve this directly. Your T1, T2, T3, 4 will come like this. Okay. Now this is for tridiagonal matrix exists for what? For a one-dimensional case. The moment you are going for two-dimensional, it will be 5 diagonal, and the moment you go for 3-dimensional, it will be 7 diagonals. So this tridiagonal technique will not apply, but Gauss elimination method would apply. Okay, that we can do. Now then, remember that this is we are doing for small cases. The moment it becomes very large, it is very difficult. So we go for iterative method, right? Now for multi-dimensional, for multi-dimensional situations, Thomas algorithm, however, is not very effective in solving the problems, and therefore we use iterative method. Now, iterative method, what do they do? Iterative methods convert implicit set of equations into explicit set of equation, and hence solution of matrix is not required. So we apply iterative method. And how do we go about doing? In an iterative method, what we do, one guesses the solution. So first of all, you have to guess the solution, and if your guess is good, then your number of steps will be smaller, and uses the equations to systematically improve the solution until it reaches some level of convergence. So you will never get the exact solution. You will stop somewhere when you will find that now it is okay, I am not improving the solution. Okay, that way. So when each variable is within certain limits, certain tolerance, you stop it. Okay. So now the advantage is this is becoming a explicit solution, which is quite fast, right, as compared to your implicit approaches, because solving the whole matrix together would be implicit approach. Thomas algorithm is converting it into explicit. Iterative methods are also explicit. Gauss elimination method is also, it is explicit, right? But that becomes too long. So now what are the methods? There are three techniques available to us. One is called Jacobi method, and it's very simple. All of them are very simple. You just focus on what I am saying. This is your matrix, this is your row, this is okay, this is your row. Now in this is your central element, principal diagonal, okay, AII. So you are talking about row I. Okay, so there will be leftwards, there will be some elements, there will be some elements on the right, and this is the row, the last known value BI. Okay, now what you do, So what we do here is that in Jacobi method we assume that nodal variables, non-diagonal matrix element denoted by J is not equal to I are known at iteration step K. So what you are assuming is that first you are making a assumption, guesswork for the thing. Whole solution is known to you, a guess is known to you. Now what you assume is that out of those known values, this, your phi I is not known. And when you are assuming that phi I is not known, all the values of phi I not equal to I, phi less than phi I and phi I more than phi I. That means on the right side, the elements on the right greater than phi I, less than phi I, they are all known. How do you know them? You have made a guess. So what happens? The k plus 1 guess is based on this kth guess. So from the previous set, you take the value of other unknowns. So you consider only one as unknown, which is the pivot element. Rest all you take from the previous iteration. Okay, and this you continue to do it. So when you have done for all the elements, then you have gone to the next step. So this way you continue. The iteration begins with an initial guess of the nodal variables, and that is called k iteration step k equal to 0. So you start from k equal to 0, then you go to k1, k equal to 1, k equal to k equal to 3. So whatever step you are, suppose you are in a 7th step and you wanting to know phi I, which is phi, okay. So phi I, let us say phi I is phi 10 you want to find out. So phi 1 to phi 9 you are taking from the 6th step, and from phi 11 onwards you are taking from the 6th step. Only you assume that phi 10 is unknown to you, and that is how each of them is revised. And so this is how we continue doing it. It is called Jacobi method. You see here that this is your column B, and these are your terms on the left of phi I, these are the terms on the right of phi I. They have all been taken on the right side. Right side means we are assuming they are known. Then you can see here the superscript on the right side is k, on the left side superscript is k plus 1. Okay, so when you are in the iteration number k plus 1, k is known to you. Okay, now in the Gauss-Seidel method, the same technique is slightly changed, and what we do here, that whatever is known, suppose I am finding in a k plus 1 step, I am finding phi 7. That means phi 1 to 6 I already know, because I start from the phi 1. So phi 1, phi 2, phi 3, phi 4. So for k1 plus step, when I am at phi 7, phi 1 to 6 are all known. So what I do, when I am finding phi 7 for k plus 1 step, the phi's on the left are taken from the current step. I have already got the latest value of them. Okay, and the remaining phi's which I don't know, I am taking from the previous step. Right? The whole concept is that all others are taken as known. In the Jacobi method, all the other unknowns were taken from the previous step. In the Gauss-Seidel, all those you have known in the current step, current iteration step, that you take as it is, and all those which are not known yet, they are taken from the previous step. So your performance improves. The Gauss-Seidel iteration is typically twice as fast as the Jacobi iteration. Okay, you reach your solution faster. Okay, and then you can decide that when do you stop. Again, you will have to decide the tolerance or the error you permit in the finite solution. So this is, you get, the smaller the acceptable error, the higher is the number of iterations. Simple, more, but still Gauss-Seidel is twice as fast as your Jacobi method. Okay, now these are the equation for Gauss-Seidel, right? You can write them yourself also. What you have done is, now I'll just show you, this is your, when you are finding x1 for n plus 1 step, b1 will be taken as it is. Now a11 we have just written here, but this is 0 because it is just to write in a matrix form, because for a computer, because this is not required, because a11 is actually on the left side. Phi 1 comes with a11. This is coming with a11. So this term is already on the left side, but we have kept it on the right side with a multiplication factor as 0, so that this term does not make any difference. But then all other equations are in the same form. It is easy to write the equation. You can write a common code for all of them. Okay, so you'll find that when you are finding x2, a22 is 0. When you are finding x3, a33 is 0. Okay. The other value is, now when you are a11, you are finding x1, x2 is unknown, x3 is also unknown. So they are nth step. When you are finding x2, x1 is known. It is n plus 1 step, current iteration. x3 is from the previous step. Similarly, when you are finding x3, both x1 and x2 are known. Okay, so this is Gauss-Seidel. If the same equation, if you write on the right side all in terms of n, it becomes Jacobi method. The difference between the two is only that in Gauss-Seidel, earlier terms which we have already calculated are taken the current value. That's the only thing. And the same thing is done for 4 equations. If you have 4 knowns, 4 unknowns, 4 equations. Okay? Again, I wish to mention here that these techniques are not foolproof, in the sense that you might get stuck up somewhere. Okay, and that depends upon the values, what values you have. So you have to be careful that you have to program it also for that if you are stuck up, how will come out of it, or what techniques to follow or what rules to follow so that you are not stuck up, which is called principal, diagonal, dominant matrix should be there. Otherwise, you can get stuck up. Now, that all thing is done by the software, right? We don't have to, but these things goes into making of software. Okay. And then there is another thing which is called under relaxation and over relaxation of Gauss-Seidel method. Now, it's very interesting. Successive over relaxation provides a way of accelerating the iteration steps. Now, you can actually increase or decrease your process of iteration by relaxation, under relaxation or over relaxation. Okay. So, if you are confident that you will not stuck up anywhere, you will like to go faster to the solution. If you think you can be stuck up somewhere, you will like to go slower. Okay. So, how do we do it? Now, when you are finding phi k plus 1, that means current value of the variable phi I, if you have finding, you have found it out, but you do not take it as it is. When you go forward, you don't take the value which you have got. You modify it. Right? Suppose phi I is, suppose you are getting in one case, in the kth, you are getting the value 5. When you are coming at phi I k plus 1, you are getting the value 7. The Gauss-Seidel will suggest you that you take the 7 and proceed. But here we are doing, we will neither take 5 nor we will take 7, we will take something in between. Right? And how do we decide? By this formula. Right? Now this lambda can have value 0 to 2. It's something like giving the weightage. So when you are moving forward, you are giving some weightage to your previous iteration also. Okay, you are giving some weight to the current, some to the previous. Now let us say what happens. If lambda is equal to 0, what does it mean? If you look at this equation at the top, when lambda is equal to 0, that means your new value is same as the previous value. That means you are not making any jump. Even when you have got a revised value, you want to continue with the previous value. Of course, you will not like to do that, because otherwise you will not improve. If you want to keep the previous step only, you will not. But that is a limit. So lambda has to be greater than 0. That means, now if suppose it is 0.9, that means, 0.1. If lambda is 0.1, you see the first equation. That means you are giving 90% value to the previous value and 10% to the current value. And you can keep on changing it. So when you have lambda equal to 2, what will happen? Suppose lambda equal to 1, what does it mean? It means that you are giving current value full weightage. The previous value will become 0, multiply 1 minus lambda will be 0, lambda is 1. So the previous iteration has no role in deciding the next value. Okay. If lambda is equal to 2, what do you get? You are getting that actually you are making a jump equal to the increase. Suppose from 5 to 7 I have got, first iteration was, or one iteration was, previous iteration was 5, the next iteration is 7. So instead of taking 7, I will take 9. जितना मेरा 5 to 7 में जंप है, उतना ही मैं एक और ऐड कर दूंगा. I will like to move faster. Because I know that I have moved from 5 to 7, so I would say that in the next iteration also I will go 2 ahead. So why not take it right now? So what I am doing, when lambda is equal to 2, then I am giving whatever you are getting to at the moment, you are adding the jump you have already taken. Okay. So this is how to speed up or reduce the thing. When lambda is less than 1, okay, you are basically giving the value to this. Okay. And lambda is more than 1, that means you are lambda equal to 1 is you are taking the current value, and lambda more than 1 is that you want to speed up even that. Whatever you are getting, you are actually want to go further more than that. So these are the techniques. Under relaxation is used sometimes in CFD solution to ensure convergence, and over relaxation is used to reduce the number of iterations. So sometimes convergence problem comes in, so you have to reduce the, you have to under relax. You have to go slowly. And sometimes you want to reduce the number of iteration, you go for over relaxation. So these are the techniques, some of the techniques to use solve the matrix which you have got. Once you have done it, you get the solution. The remaining part is putting that solution into pictorial form, CFD. So that is called post processing. Once you have got the answer, you convert that into graphs and into diagrams. Okay. So this is the complete process. So once the matrix is formed, you have to solve the matrix. And the methods we have Gauss elimination method, TDMA, Thomas algorithm, or we have iterative method, Jacobi, Gauss-Seidel, and under relaxation and over relaxation of Gauss-Seidel. This is how we go about doing it. Okay.